Great. Welcome everyone for today's webinar. I think we're just going to give everyone about 30 more seconds before we start. So just bear with us and we'll kick off shortly. Great. Well, welcome everyone to today's 11th SWAN Americas Alliance webinar entitled Data as a Service, the Key to Improving Water and Wastewater Management. Generally, what we've seen with increasingly advanced solutions in the water and wastewater utility industry, data as a service is becoming increasingly central to operations, and that's one thing that we want to examine in today's webinar. Just a few quick housekeeping items before we start. There will be a Q&A session at the end of the webinar. Do feel free to submit questions through the Q&A function at the bottom of the webinar screen. There may be some answers from panelists during the webinar, or otherwise we will answer those at the end. We'll save about 15 or 20 minutes for discussion. This live webinar is available for all to join, but it will be recorded and made available to SWAN members who want to access this later on. We are using Zoom for today's webinar. As part of the format, each speaker is going to share their screens through the presentation. This may add a few seconds just as we switch over, so please do bear with us. Now for today's lineup. In order of speaking position, we have Patrick Kiley, CEO of SENTRY, Camilla Braithwaite, Project Manager at Rezatec, and Tim Ruggeber, Director of Engineering at Xylem. We're really very appreciative of having our speakers with us here today, and we look forward to understanding how they see data as a service, how they've used this as an opportunity to engage customers, and how water utilities can benefit from data as a service more broadly. Before we dive in, I just want to take a minute to review current Alliance activities and upcoming events. And so for those joining us today who are not members of the SWAN Americas Alliance, we do want to take a moment to advocate for membership. It's a great time to be taking a leading role in advancing smart water and wastewater. The Alliance helps members to collaborate with fellow industry stakeholders, share valuable insights between and within our subgroups, which are focused on outreach, events, partnerships, and research. Here's just a quick snapshot of the Alliance's member base, and it's a great industry engagement with an array of utilities, industry partners, and academics. Our footprint spans both North and Latin America. We're very proud of our members and want to ensure that our activities and engagements reflect the water utility landscape's interests and needs. So a thank you to all of our members, and we look forward to those that join us in the time ahead. And just before I hand off today's presentation to our first speaker, I want to thank all the members and attendees of SWAN's 10th annual conference. As you can see, there are over 400 attendees from 32 countries, 25 utility speakers delivering excellent insights into their activities in smart water and wastewater advancement. SWAN members can access the conference materials for free in the member zone, and non-members will soon have the ability to purchase those through the website. And last, I quickly want to make everyone aware of the upcoming AWWA and SWAN International Smart Water Symposium. This is going to be held on November 10th and 11th. While originally it was set to place in Austin, Texas, this event is now going to be online. Do stay tuned for registration and agenda announcements. At this point, I'm happy to pass things over to today's first speaker, Patrick Kiley. Patrick, please take it away and share your screen.
Thank you, Seth. Okay. Okay, is my screen up?
Yes, it is.
Oh, good. Okay. Thanks very much, Seth. This is super exciting. Really looking forward to maybe introducing SENTRY to a larger audience. Okay, so the first question really, I mean, why are we here? What is the problem we're trying to solve? Or more importantly, why are we even talking about data as a service? Why is that a thing? I just pulled this report up. It's a SWAN report from 2017. This is a survey of 23 global water utilities, looking at like what are the biggest barriers to these utilities actually implementing big data or using data perhaps I mean, a better way of maybe talking about it is how can people use big data, use data to optimize process, improve the performance of their facilities. And I picked it out. I mean, it is the highest one, but data quality seems to be a standout one for us. And with SENTRY, this is the one that we've really been focused on trying to solve with our SENTRY platform. So I'll go into it here, but really the next question is, well, why would you provide that as a service? And from our perspective, sometimes it's about risk. And as the company, I feel like we can better take that risk sometimes, and we can provide data and make sure that we provide high quality data to our clients. Okay, so in terms of the problem statement, why does data, why does data not always work well? So we know that to operate, in this case, a wastewater treatment facility, you need good data to understand what's happening. You have fluctuating incoming wastewater streams. Potentially there's toxic compounds in your wastewater streams. And we know that existing sensors and existing types of data that you can extract from wastewater tend to have a very high O&M requirement. Sensors themselves, typical sensors, perhaps they're light-based. You have to put these sensors into wastewater environments. That doesn't tend to be a suitable environment for long-term stable performance of those types of equipment. So that's the key question. Can we provide long-term, reliable, robust data that operators at wastewater treatment facilities can provide actionable, intelligent, or make actionable decision-making based on that data? And can you do that in a low complexity, perhaps low maintenance way? And then can you then take that risk off the client? Can you take that risk off the utility and provide that data as a service? And does that, again, reduce those barriers to those operators in those facilities getting data and leveraging good data at their facilities? So what we did at SENTRY is we kind of flipped the sensor technology backwards in a way. Instead of looking at sending light signals into wastewater and trying to understand how the chemistry of the wastewater is changing, what we've done is we've developed a novel sensor platform where we take active biomass, active biofilm, we install our sensors, and we prime the surface of the sensors, those conductive surfaces, so that active biomass in the environment can grow on those sensor surfaces and use those sensors as a source of respiration or as a respiration sink. So we take this information directly from the biology and we send it to a cloud, or we can send it on site to the locals, to the on-site SCADA, but basically taking the blindfold off the operators. So now the operators have a visual tool where they can see in real time the metabolic activity of the biomass right the way through their wastewater treatment process. So it's a novel technology. We provide it as a service. So we don't typically sell equipment. We typically provide equipment and allow operators to use that equipment to see what's happening in their process. So that's one step. I mean, developing a new technology, developing a disruptive technology, providing a new type of insight to your process is just the first step. Over the last 2.5 years, we've been deploying commercial systems. This is like an overview or a map of where we install sensors at wastewater treatment facilities. But more importantly, what it does is it outlines the different problem statements that we look to solve. So for us, a typical wastewater treatment client will take sensors and they'll first perhaps install them at the influent of their wastewater treatment plant. So they can then profile exactly what's coming into their wastewater treatment plant, how it's impacting their biomass. If there's potentially something toxic in the wastewater stream, they might go further upstream then, put more sensors into the collection system, try and pinpoint exactly perhaps where those toxic events are coming from. Perhaps it's shifting organic loads and you want to identify who's discharging that organic load into the collection system. Or clients of ours will go downstream. So this is where they will, okay, well, we want to understand biological activity. We want to understand the rates at which our biomass is consuming carbon. How can we leverage that information for perhaps understanding aeration optimization? Can we use that information for better nutrient removal? Or can we use that information to understand what the water quality is leaving our wastewater treatment plant? So that's at a high level, the types of problem statements we look to solve. I'm going to go through maybe 2 case studies or just talk briefly about 2 different applications. So this is one in Canada. This is a city of Charlottetown. Charlottetown, we did a 12-month project with them. They have some industrial clients in the city. They also had intermittent issues with their biological process. They could never really pinpoint exactly when things were going wrong or when things were going well. But certainly we installed sensors at the primary clarifier, the wastewater treatment plant. And basically the sensors are primed. They're sending that real-time information, as you can see here in the top right. The moment anything toxic comes into the wastewater treatment plant, so it's in the wastewater streams, the operators get a real-time notification. So this is one event. It's Monday. You see a rapid drop in activity. The following Wednesday, a very similar response. The operator would get notified of this in real time, and he would be able to go and take a sample and certainly go and then try and deduce who in the collection system might be discharging at this time. But also, because we're generating data over extended periods of time, we can generate really nice statistical analyses of those data and pull out, for example, down here, it's the average weekly trend at that facility. So we can provide this to the operators, perhaps a couple of months after our sensors are first installed, and they can see very clearly when the organic load is coming to the plant, when the biology is most active, and when perhaps it's not very active. So a second example, so that first one really is revolving around, toxicity, something strange coming into your process, being able to identify these events the second they're happening. This second problem statement, we worked out with the city of Summerside, again, a Canadian utility. This is a really great project, a 5-stage Bardinfo process. And it was really interesting. The client had intermittent issues with nitrogen on the effluent. But again, they just couldn't put their finger on it, and they couldn't really understand, well, when are things not working well? When are they working well and when are they not working well? So we have sensors installed through different parts of that 5-stage process, up front in the anoxic zone. So basically we could understand and profile how the activity of the biomass in different parts of the process was changing over time. Top left, we have the weekly repeating trend from the anoxic part of that process. So very clearly it points out that Thursday, something very strange is happening on a Thursday, recurringly. So, well, what does that mean? So then you can go back to your process and try and figure out, well, from a process perspective, what are we doing differently on a Thursday that might be causing that to happen? Also, we had a couple of events through the year where we had big spikes in nitrogen on the effluent, and we really couldn't understand why it was happening. But then when we went back and understood the different stakeholders that were involved, the different industries that were discharging into the collection system, we identified one industry in particular, a dairy in this case, that was discharging or contributing a significant amount of carbon to the incoming wastewater stream. And we could very clearly see that when this particular client was not operating or when they were shutting down for a period of time, that's when the client, the wastewater treatment plant, was having issues with their nitrogen on the back end. So again, having reliable data, us providing that data as a service, not necessarily just giving equipment to someone and letting them, use it themselves, but us working with the client over that 12-month period really allowed us not just to provide them data, but help them understand what the data meant for their process. So here's one closer to home, perhaps in the UK. This is my last example, but just how has COVID impacted some of our clients? What does that mean for operations at a wastewater treatment plant? This is a Wessex Water. It's one of their wastewater treatment plants. Because we have the sensors already installed, we had a very good idea of the incoming wastewater to that facility, and we had a very good idea of the typical weekly pattern that would come to that facility. So you can see here pre-COVID, the yellow line, very regular during the week. Something strange, perhaps, slightly different on the weekends. But then post-COVID, we had a big change, certainly on the weekends. So you have people moving, you have industries changing. All of this is changing the wastewater composition, perhaps even changing wastewater flow. But us being able to provide a service, it means that we're on top of this. It means that when things change, we can help our clients understand what that means, and we can be sending them notifications in real time as to when we think things are important and when they should be aware of them. Fantastic. Okay, so the the SENTRY platform, we have chosen data as a service as our model. Really, and it targets the first one there. We don't want barriers between ourselves and our customers. We don't want to just give equipment to someone and have them try and figure it out and, you know, have all of that risk, whether it's the capital purchase of the equipment or whether it's just the time and resources that are required to install, operate, maintain, all of that. So we've tried to reduce those barriers, and we do think that providing our equipment and our technology and our monitoring solution as a service is the best path for both parties, both the technology company, the supplier, but also the end user and the utility. And I think that's it, Seth. So I will hand off next to Camilla. Thank you.
Right, can you see my screen?
We can see it, Camilla, but if you're able to go to full screen, that would be useful.
Is that working? That is what I'm meant to be doing. Let me see. Try again.
Sure.
No, that should be better. Is that better?
Perfect. Thank you.
Lovely. Wrong screen. Sorry. Okay. Thank you very much, Patrick. So thank you to all of us for joining our session today. And thank you to SWAN for having us on your webinar series. I'm Camilla. We provide powerful products that address our customers' challenges. And data is obviously a key challenge for customers. McKinsey Global has a piece of research that show how successful and resilient data organizations are these days. So every organization operates on gut instinct sometimes, but data-driven organizations don't suffer so much when there's an issue like succession issue or significant change. So data-driven organizations they'll have greater consistency, greater transparency, and they'll have a better understanding of their decision-making process. And it's easier to see what works and what doesn't work and support faster decision-making processes. So data-driven decision-making requires the right data, the expertise to analyze it, and the technology to build it and share from. So if you don't have some or any of these, then using data as a service is a good way to efficiently bring that kind of intelligence into your organization. So Rezatec are award-winning geospatial AI solution providers. We were founded in 2012, and our team has grown to 50 people, and that includes some PhD data scientists and Earth observation experts. Rezatec serves 4 key verticals, but energy being one of them, agriculture and forestry, but water utilities is what I'll be talking through today, just to show you the capabilities of how satellite data analytics as a service to you can help prioritize expenditure for water asset management. So what are the challenges that we can help water utilities solve? So as water pipelines are buried underground, having visibility and understanding of their state of repair is extremely difficult. So water pipes age and corrode at different rates depending on their material, their diameter, the soil they're buried in. And for those utilities responsible for dams, visibility is still a problem as they're often in remote or difficult to access locations. So without visibility and understanding of your asset base, it becomes harder to pick up problems in time. Not only are water utilities struggling to respond to bursts and address leaks, but they also need to consider longer term upgrade planning. Effective replacement programs can reduce non-revenue water, but digging out perfectly good pipes is a waste of effort and resources. So you need to get the balance right there. And there's growing regulation around both water networks and dam management to help prevent failure. So with climate change, utilities have more extreme droughts and floods to take into account. And the consequence of failure of a water pipeline can be pretty high in terms of resulting flooding and infrastructure affected. But for dams, it can be catastrophic. So water utilities have a duty of care, and regulators are stepping in to increase penalties and fines. So here's a bit of how satellite data can help inform decision making. So really since about 2016, there's been a genuine evolution in the capabilities born out of source material satellite technology. And that's really able to benefit water utilities now. Rezatec combines advanced AI analytics, numerous other source data inputs as well, and we help provide our clients with detailed, highly accurate data analytics across their entire right footage, and our platform's entirely agnostic to the sources inputted, meaning we always acquire the most appropriate data. So whether it's from multispectral optical indices or from radar, we can also combine it with other data sets such as aerial imagery, environmental data, weather, as well as existing or historic data from the client about the clever stuff that our data scientists and Earth observation hang on, sorry, go back again. There we go. Sorry, I had a notification. So let me dip into this clever stuff that our experts use. So I'm using an example of synthetic aperture radar for ground movement detection. There are two main advantages of synthetic aperture radar: the ability to look through clouds and the fact that it can be operated at night. So these solve the issue of regularity of updates that optical imagery would have. Historically, the European Space Agency has maintained SAR satellites from early 1990s onwards with ERS-1 and 2, and later then they had the Envisat missions. And we still have access to this archive of information if we need it. However, the most recent European space station, Sentinel-1, launched in 2015, and that offers better resolution of 50 meters and a better revisit cycle ranging between 6 and 12 days, depending on where you're based. So because of this data being available for a while now, a number of techniques have been developed to look at the phase aspect of the radar signal. And phase aspect is one of the two components within the data set, and it's what makes the estimation of ground motion possible. So when our experts look at a phase data set, they're comparing the difference between a location on one phase wave at two different times. And this forms the basics of what's known as Inferometery. So this is shown on the right-hand side in a form of a colourful image, which is an infogram. And the comparison between two dates of the phase, but it's in a raw and quite a noisy state. So we then use further advanced techniques to clear this data, and then so we can begin to extract the phase signal that's related only to the ground displacement. And this then provides the basics to our ground motion analysis. So this is an example of how the data can be visualized. This piece of analysis comes from Los Angeles. Our team cleans up the data, they remove the noise so it's easier to understand, and the blue color that forms the center of the right-hand side image here corresponds with uplift. And then all the orange and reds are areas of moderate subsidence, similar to the Las Vegas map. So what's interesting in this example is the fact that the transitions between the areas of uplift and the areas of subsidence align with the purple lines, which represent fault line area, helping validate our technology. So techniques from the previous slides can be readily applied to dams and reservoirs and to urban or rural water pipelines to model structural movement. So we can also complement the ground motion with vegetation monitoring, but that uses analysis of optical data from satellites, which provides information on vegetation vigor and moisture, and that's a proxy that we use for seepage. So this is an example of our dam monitoring product, which is used by Hunter Water, based in Australia. Like many dam operators and owners, they use engineers, or they used to use engineers visiting their dams to monitor them. And Dan from Hunter Water told us 800km/h road which runs across the top of it. And so in order to survey the dam once a year, they have to shut it. So this dam at Grahamstown holds nearly 82,000 million litres of water. And they wanted, so they were concerned with it, and they wanted to monitor it more frequently. So typically we would first create a signature baseline analysis for the dam by reviewing a few years of retrospective data, and we'd analyse how each structure behaves through time. So that's taking into account factors such as water level change or seismic activity. So in this example, we used 4 years of data in our analysis, and that helps create a baseline for what's normal seepage or what's normal moisture levels. Then we use the baseline to set the threshold for what an anomaly is. So our subscription provides monthly data, and the analysis updates which use this baseline to notify teams of an anomaly going forward. So the dam operator can then review the data, and then if they feel they need to, they can then arrange a site visit. So in our initial analysis, we were able to detect settlement in one area, which Hunter Water confirmed was due to groundworks. And we also identified an anomaly in the vegetation figure, which was actually down to grass reseeding rather than seepage. So there were no other worrying issues, which Hunter Water were pretty pleased about. So there are 3 main areas that we can help dam owners and operators with. Remote monitoring improves the safety of operatives and reduces the chance of dam failure as well. The automated monthly updates help the engineering teams identify issues earlier, and it helps them prioritise where they send those surveyors and engineers to and when. And it also improves operational efficiency. So for one of our clients, they have 100 dams. The cost of a site visit is $2,400, and they were able to reduce that from, they actually had monthly visits, so they were able to reduce that from 12 to 6 visits a year. And that roughly equated to about $1.4 million in savings. So not only does Rezatec's solution cost far less than that, obviously, but we can also offer kind of consistent measurements with millimetric precision on a monthly basis. So our solution spots issues such as an increased elasticity that simply cannot be picked up by just someone coming and checking on it with the traditional sort of walkthrough. So we also use ground motion and vegetation monitoring to provide intelligence on water pipelines. However, for this type of asset, we use much more asset data from the client in our model. Utilities Kingston is based in Canada, and they use the intelligence that we gave them to prioritise future inspection, detection, and the maintenance activities in a much more cost-effective way. So for them, for any client, we can combine 2 to 5 years of historical failure data with asset information like the material, the diameter of the pipes, the age of the pipe, with our information on ground motion, moisture, and vegetation vigor. And the analysis is done we break down the pipe into short sections and do the analysis on maximum of about 100 meters long. So we can then produce a likelihood of failure that is quite specific, and maintenance team can then use to identify a leak or a burst. And then we also include further data sets that provide a cost of replacement based on the types of roads, the buildings, other types of customers, and how much it costs to dig up that particular pipe and replace it. So that gives a holistic value of the probable cost of failure for each section of pipe. And that's really powerful, because then you can help prioritise your replacement programme according to the probability of failure and the consequence if that failure were to occur. So we initially tested the model with Utilities Kingston. They had 3 years of data. We trained our model using the first 2 years, and the client kept the 3rd year of data back to validate our results. And our pipeline solution of the top 20% of high, we're able to identify where failure is most likely to occur. In the 60, we identified 60% of the pipeline failure for that third year. And for another client, this was closer to 70. So by prioritizing upgrade programs, our pipeline risk solution can help reduce the capital expenditure. It can also help support a more data-driven approach, for example, by prioritizing where you put sensors or loggers. And it can also inform where engineering resource could be deployed to fix bursts of leaks faster. And it can change your operations from a sort of much more reactive approach to a proactive model, which helps you get ahead of failure before it happens. So I've given you a bit of a snapshot and run through of what satellites can do, what satellite data can do for water utilities, and the data analytics that can help you hopefully make more powerful decisions based on data. So if you want to know more about that, here are some contact details, or post a question in the chat. And with that, I'll hand over to Tim.
Great, thank you very much. All right, are you able to see my screen?
Yes.
Okay, fantastic. So my name is Tim Rugaber. I am with Xylem, particularly with the digital solutions part of Xylem, where I focus on wastewater network optimization and decision science. Xylem historically has been focused on pumps and treatment systems and these larger pieces of infrastructure. But recently, they've been really focusing on what's the analysis. So part of data as a service then is really analysis as a service. So how do we actually use that data to help cities, municipalities be able to actually operate their collection system? So with the, within collection systems or wastewater networks, this is a very difficult area to work because it is not only corrosive and underground, but it's also extremely dynamic, with huge slugs of water, big surges happening every time it rains, particularly during large storm events. Operators, some of them are operating blind, some of them are operating the system based on 30 years of experience and just have that trained response for how things work. And some of them are just getting raw data values that are playing to them. They're having to figure out how all of this fits together in real time under very stressful circumstances. Fundamentally, what they're trying to do is understand what's going on right now and what will be going on in the near future. That near future part is interesting for a couple examples. So one of them is to be able to, look at conditions where we have very long lead times. So we have a travel time where if you make a change to an upstream pump, it could be several hours until that impact reaches you downstream. Another one is actually where there's extremely short travel times, where their drop of water hits the ground and then goes very quickly into the sewer and very quickly through the system. And you have to almost proactively operate the system in anticipation of that rainfall coming. So how do you do this? And how do you operate it under all these different conditions that are always changing? Fundamentally, how do you make a navigation app for sewers? And that's fundamentally what we're doing. So a navigation app takes real-time sensor data, how fast your phone is traveling down the road in your car, takes information about where things are not behaving as they expected, where there are blockages, where there are constraints, runs it through a model, and runs it through an optimization algorithm. And then it comes out with a route that tells you to turn right in 500 feet. Now that route is going to be very different at 2 in the morning compared to rush hour because your conditions are always changing. And that's exactly what happens in wastewater networks during storm events, is that your conditions are always changing. And you only have to work on what's going on right now, but what will be the impact of that when the travel time is taken into account or when the rainfall comes. The example I have up here is one of these operational dashboards for Oraloma Sanitary District in California, where we're looking at, they have to coordinate what's going on several hours upstream with how much flow to send to storage, with how much flow to send to the plant. So we're looking at multiple different scenarios depending on what rainfall is going to be coming over the next 12 to 24 hours. And we have to make decisions based on that as we're doing it. So to do that, we need to have a very good model of what is that rainfall going to be coming in there? We can look at real-time data right now to understand what's going on, but we need to look into the future. We need some sort of model. With the models, so let's start with looking at what's going on right now. So this is the first level, basically giving you just a screenshot of where's the traffic on that navigation app. This is a system we developed for South Bend, Indiana. This is the interceptor line that comes along the main part. The green is the surface level. Operators to go out and say, okay, we need to close down roads. We need to make sure that we take care of this flooding. But then we also have the valves opening and closing. And we can understand, okay, is everything operating as we're expecting? Is there more we could have done within our control system? Now, if you look at it even just as a hydraulic grade line, where are we right now? You start to see some interesting things. You start to see some discontinuities in what you expect with the HGL. You see where some grit deposition was. You see a construction problem of how a pipe was put together. And you see suspected grit that you need to go out and resolve. This is all useful and good, but that doesn't really help us with, okay, what will be coming? Where does the future happen? The future happens, you need some sort of model. A standard hydraulic and hydrologic model, referring to hydraulic is the flow within the pipes and hydrologic is the weather component of flow coming, hitting the ground and going into the pipes, is where things have started historically. And this is useful, but there's some shortcomings to that. When you're creating a model, the hardest part is trying to figure out how much of a drop of rain is going to be hitting the ground and then going into the sewer. And when is that drop of rain going to be going into that, and how much of that drop of rain is going to go in the sewer? So there's a lot of uncertainty, or you inherently have an abstraction in there. And this is also heavily influenced by antecedent conditions. So this requires a very costly calibration, which needs to be redone every few years. And even then you have a model that can take multiple days to be able to do. Hydraulics aren't really going to work under that, particularly if you have to run thousands of different simulations so you can know what's going to be happening with certainty in the next 15 minutes. So to do that, Xylem's developed a machine learning enabled analysis called CHRIS, which stands for the Cognitive Hydraulic Response System. This is an artificial neural network that correlates rainfall to sewer flow using historical data. And what we do when we have these two combinations together is we're able to understand for a given rainfall, how's it going to get to an actual flow, and implicitly taking into things like antecedent conditions, groundwater changes, all those factors that come in there so that we can really have an accurate model that comes at the end. And it's a very quick model that comes in the end because we're not needing to represent all this hydrology and hydrologic components of the system. We're able to simplify that all into a neural network. So let's look at how this is done. So this is the measured flow that we're going to use to validate how good our CHRIS model works. So we have our CHRIS model, it's been trained with 10 events. And we can see, we start seeing some of the catching the peaks, but it definitely needs some improvement. 12 events, getting better. 19 events, even better still. By the time we get to about 3-4 months worth of data, we are able to really capture that well. And we can capture the fact that there's back-to-back storms. We can capture variances in groundwater infiltration. And this keeps getting better as we collect more and more of that data. And we can feed that into the model, continuously train that model to get that more and more accurate system while still being able to get the quickness and the response of a very quick model as well. And it can capture those back-to-back events even as we're looking over several days period of time and be able to be very, very accurate in that, both in terms of volume and in terms of peak flow. Fundamentally, why does this matter? So we're dealing with wastewater networks that are here. The increased accuracy is leads to typically less requirement for new infrastructure, particularly when we're dealing with SSO and CSO communities where they have to build new infrastructure to be in compliance. When we applied this methodology and been able to create that full digital twin, we were able to save one utility about over $200 million in prevented capital improvements by just having a more accurate model. That is still going through negotiation, so we're not able to mention which one. But that accuracy combined with the faster analysis really gets to be an interesting thing that we're using for these operational support systems. So for San Francisco, we're coordinating several huge storage tanks and providing insights in how to balance these 10 locations and how to move things around. What's interesting with that is the very, very short amount of lead times that we have. So a drop of water will hit the ground and within a matter of minutes could be at the tank and then they need to move down to the wastewater treatment plant. Well, these tanks are also tens of millions of gallons. So if we need to dewater these, we can't wait for that rain event to come. We need to be proactive in that to make sure everything is treated as much as possible. So this is where we have thousands of simulations going on with all the different rainfall possibilities and all the different control algorithms of how we can balance things working together to be able to maximize capture at the wastewater treatment plants, maximize capture in the tanks, and then minimize overflow out of these tanks. They're called transport storage boxes. Columbus, Ohio, very similar. We have storage tanks, we have upstream storage areas, we have 2 wastewater treatment plants, and we have a high rate treatment facility, all of which we have flow that's coming into the system, and we need to balance that. What's interesting in that case is we have several hours of travel time between when we make a decision to send more flow downstream and when that flow hits downstream. Meanwhile, other flows from other areas are also coming and hitting it. So by being able to look proactively into the future with these analytics, we're able to get better capture and better treatment of the wastewater. So this is again important because we can use the real-time data to understand what's going on right now, and then the analytics as a service on top of that to be able to give those further insights that can only be captured as a matter of experience in looking at these data streams for hours at a time, for years at a time. But about a third of utility operators are able to retire within the next 5 years. So that level of experience is something that is at risk for a lot of utilities. So having this type of approach and taking these control algorithms and these insights based on these analyses, being able to use that to train up the next set of employees and operators even faster and start getting them some of that tribal knowledge. But fundamentally, it all starts with data. Now that data starts with initial conditions and that's continuously updated. But the analysis is needed to get the full value from that. That can be using existing data streams from existing SCADA systems or new ones that are added in areas where the city or utility previously had no insight of what could be used. One of the things though that is very, very important, and one of the things why data as a service is also very important, is that validation of the data as it's coming in. If we are making decisions that impact whole utilities based on these data streams, it better be accurate. And so we go through a real-time validation process of the data that's coming in to assure its accuracy based on how it's acted previously, so that when we move forward with that, we can be confident that we're making decisions based on actual conditions in the system rather than a faulty sensor reading. And overall, better data is going to equal better solutions every time. So with that, I'll head back to you, Seth.
Great, thank you very much, Tim. So what we'd like to do at this point is just to open it up for some questions and answers. So feel free, if anyone has questions at the moment, to type them into the Q&A box at the bottom of your screen. We do have some at the moment, so we can start to look at those and have a bit of a discussion. I know a couple got answered just in text, but it may be good to talk about those out loud as well. Patrick, you got a couple of questions just looking under the hood a little bit in terms of some of the operations and maintenance, looking at the split between installation services, hardware, data services. Could you speak a little bit to the response that you gave, Will?
Yeah, okay, so Will was asking, In terms of the cost, what is, I think maybe more on the client side, what cost are we trying to eliminate? So the answer is both. So the first thing we did, because we provide a service, we put the onus on ourselves to develop a sensor platform that didn't have the same issues from your traditional light-based sensors. So it being a biofilm-based sensor means you can place it in the wastewater. It's just a flat surface. We want biofilm to grow on the surface. We want it to be representative of your wastewater environment. So we specifically ask people not to clean the sensors. So you put them in there, you let the biofilm grow in it, and you leave it there. What we do ask is that every 3 months, there's a visual inspection of the sensor. So you pull it out, you just visually look, make sure there's no rag on it, obvious ragging, but there's no cleaning. So that's one massive O&M issue that you eliminate, because that typically is the issue from operators, that's the complaint. It's, oh my God, it's another sensor, it's another thing I have to clean, it's another job I have to do. So if it's low maintenance, that's certainly a bonus. And then on the cost side, the industry standard is to sell equipment, and it's to sell sensor equipment. And, you know, there's numerous examples I've seen where sensors tend to be used as door weights as much as actual sensors in wastewater environments. So by providing a low barrier, so we're not asking for, you know, a significant capex upfront payment, we can get you the equipment in your hands, and then the onus is on us really to demonstrate the value and continue to provide that value with the data.
Perfect. Thank you. Camilla, I may pass this question back to you as well. So a question came in thinking about underground pipe leaks. How much water does it need to be, and what size of an area can be identified?
Yeah, so we don't actually identify a particular leak. We're not looking at the volume of water. We're not looking at, you know, we don't have to have a certain amount of water there to be able to spot it, because what our solution does is a risk-based analysis. So we take lots of data. We take the satellite data, we take ground data, we take your pipe data and historic failure data, and we create a likelihood metric. So that is saying that where on your network you are most likely to have a pipeline failure. So by dividing the network up into quite small sections for this analysis, it means that you'll have a section of pipe that has a high likelihood of failure metric, which allows your teams to identify that quite easily, so that you can look at it across the whole network. So you can identify particular pipe sections, or you can then look at a particular DMA. So if you're saying, right, this DMA has a district meter area, it has definite lots of leakage, there's a lot of non-revenue water here, then you can prioritize within that DMA. So then you can say, okay, we think the likelihood of failure is high in these particular areas, and then you can prioritize your teams, which then helps save you money in terms of not having to dig up perfectly good pipe, but also digging up pipe at the right time, so before it fails.
Perfect, thanks. Tim, just to throw one your way as well, we've got a question here asking whether Xylem provides the field monitoring for the calibration stage of the neural network.
There is, so that is an option in there. So we do have the ability to be able to put out real-time telemetry units, monitor what's going on there for that calibration or that data gathering phase, as well as be able to use that for the real-time operations. However, if there's already something that's in place, if data has been collected, or if it's already put into a platform that we can use for real-time operations, we'll use that data as well. So there's a myriad of options depending on what's in place and what the needs are for that particular utility.
Great, thank you. And maybe one for the panel. So we've got a question here thinking about consent decrees. And so asking, shouldn't the EPA require all consent decrees to have a digital machine learning solution? Can an existing consent decree get renegotiated based on these findings? Also, consent decrees create a big price tag and therefore affordability concerns. Any thoughts there in terms of managing consent decrees, how digital solutions, machine learning solutions can really help to fulfill those obligations, and maybe think about renegotiating some of those specifics?
I'm currently in the process of working on several consent decree renegotiations based on these types of methodologies that I was talking about here. I can't talk to specifics because they are in negotiations, but what we've been able to look at is by looking at how you operate everything, you can be much more effective with the infrastructure that you have in place and the infrastructure that you're going to build. And that drastically reduces the amount of infrastructure that you need because everything is fully utilized to the maximum extent possible. Similarly, by looking at these analytics are a key component of that, improving that model and improving the operations based on these analytics, again, drives down that cost typically, or at least squeezes out the uncertainty from the models upon which these consent decrees are based. I would love it to be a requirement, but what I'm seeing here is that there's a huge opportunity. And I've seen that in every utility I've been working with.
Perfect. Any comments from the other panelists, or was that a pretty well-rounded response? Okay, so that's looking pretty good then. Camilla, one here for you. How many different variables are taken into consideration for the pipe risk analysis? Can you comment on that a little bit?
Yeah, absolutely. So we take the pipes themselves, so information about the diameter, the material, and the length of it. We also look at the historic pipeline failure, so where a utility has previously failed, and that is useful for training the model. So we also bring in our ground motion analysis and vegetation analysis. The vegetation obviously being a proxy for any leakage that might happen. And we can also incorporate soil types and the soil moisture, and because obviously that has an impact on the pipe itself. We can bring in further details around the cost, so we can create cost estimates of how much to dig up a pipe, but actually on the whole, utilities will already have this historically, how much it costs to replace a particular type of pipe, and then we can look at road type, building type, and we can allocate a cost according to that. So essentially, we can incorporate a lot of data in there, and the more the better. But if you're short on data, then the historic failure and just the types of pipe, material and diameter are the minimum that we'd require.
Thank you for that. One question, Patrick, a little bit earlier on is just specifically about how you mentioned that the service and equipment may have a lower O&M. And do you have any comments maybe in terms of monetary value on that, or maybe something a little bit more broadly to comment?
Yeah, I guess I did and I didn't. Yeah, I mean, as I said, you know, the O&M for us is paramount. So making sure that operators don't have a massive another thing to do on their list. So to be honest, once sensors are installed, so it takes about 2 or 3 hours to install a proper sensor, you know, 2 sensors, a control panel, it's an end-to-end solution. Once it's installed, the sensors are pretty much forgotten about straight away. And after that, it's the dashboard. So after that, the sensors are in, the data is going, and the only interaction, or the most interaction the operator will actually have, or the process specialist will have with the platform, is on their phone or on their laptop. So they'll get a notification if something strange has happened to the biology. They'll get a notification if there's a big slug of organic load coming through, or they'll get a notification if there's something acutely toxic in the wastewater stream. And that's really how they interact with it. There's not a lot of hands-on with the sensors themselves. They just become part of the process.
Okay, and building on that, there was another point actually, in asking whether recommendations or messages sent to the PLC are actually to perform a process treatment action, or are all the kind of decisions left up to the operator? And that also may be getting into a larger question around, you know, where we could be versus where we are today, and how's that all moving and shifting?
And exactly, and there's different levels of complexity. So the first level for us at least is, we have sensors, they're part of your process, and they're taking biological activity and they're converting it to a digital signal. So at the very base level for us is, we almost have this always on alarm system for your biological process. And that for us is enough if the operators are worried about change and if they're worried about fluctuations. So it can be simply the biology is telling the operator, look out, something just changed, let's maybe investigate that. Then the second level, and usually for us, maybe it's 3 months later, maybe it's 12 months later, where the operators and the process people are very familiar with the data, they understand it, they now understand the benefit, and then they'll start looking at, well, can we use this data? If this data is coming from a primary clarifier, can we use it as a feed-forward signal to understand the aeration demand of our facility? Can we put it in a D-night system? Can we dose carbon more appropriately into our D-night system? So it really depends on the process and depends on the level of complexity on site. But yes, the short answer is it's a signal. It can go from the sensor to on-site SCADA to make decisions just as easily as it goes to the cloud.
Perfect. Tim, this one's for you. Does Xylem offer a similar model to Island in that it retains the ownership of the sensors, RTU endpoints that are installed as the data collection layer of the data as a service offering?
We do have that option. A lot of the utilities I've been working with, though, as these are intended to be permanent monitors for long time operation, they'll actually buy the equipment and install them, and then all the maintenance and the subscriptions and everything on top of that are after that. So we've done it both ways, but the latter is what's been typically used, at least in the United States so far.
Great. Okay. Maybe one topical question for 2020. What impacts is everyone seeing with COVID-19? These technologies seem to address both workforce training and protection and operational resilience. But any comments really when it comes to how your organization is seeing COVID-19, how you're able maybe to help respond or kind of plug into that?
I'll maybe go first, if that's okay. From our perspective, it really depends on the resources that are available on site. You know, let's be honest, for about 4 months, no one could do any more work, any additional work on site. It doesn't matter how functional it is. But we think that we're on the right side of this equation, being able to monitor your system remotely, being able to receive alerts for you to be better able to address issues the moment they happen, and deploy resources when you need them, not just because you have to do it every morning as part of a protocol at 9 o'clock, Monday to Friday. Being able to deploy resources based on actual events. So we think going forward that the transition to data, the transition to service-based business models will only increase.
Yeah, I think having access to data to make decisions remote helpful. I think we've obviously seen that that actually, because we're using satellite data, that is a very useful way to take decisions that using data that's completely remotely collated and can be frequently looked at. So that's one thing that's sort of that our clients are seeing and finding useful from us. But I think data-driven decision-making helps you adapt very quickly to changing environments. And that's the thing that happened with COVID, was everything changed overnight. I mean, I don't think we've ever seen anything change so quickly. And if you are more agile, you're more able to plan and adapt to those changes. So I think that's where people who have had access to data-driven decision making have been ahead of the curve. So and others who hadn't are seeing the benefits that they want to tap into.
Great, thank you. Tim, did you want to comment, or should I move on to maybe a final question for everyone?
I think everyone else captured it really well. I'm seeing the same thing.
Perfect. Okay. So one quick thing just to highlight to everyone attending, in the chat box, there's been shared a feedback survey. So please do chime in there and open it up and give your feedback. One last question for the panel before we wrap this up is just really thinking about some of your final thoughts with data as a service. Maybe where are we today? Where are we going? How do you see some of the kind of futures of data as a service and working with water utilities?
Yeah, I'll maybe touch it first. Everyone all these utilities, everyone's super busy. Like nobody has time even now, you know, it's just really difficult. So allowing outside companies to provide service and provide this insight that makes people better and more efficient at what they're trying to accomplish, I think is the path forward. So we're happy that we're taking water quality monitoring and trying to do that in a more effective and more efficient ways for our clients.
Yeah, there's also a lot of skill in wrangling a lot of data. So there's that sort of people, process, technology thing that, you know, having the skills in house is to get that. It can take a lot of time in itself, but having data as a service, you kind of can purchase a slice of that works for you, and I think that has real benefit. So you get the data that you need, you get someone else to look after it and have all the hassle of making sure it's safe, and then also the analysis on top of that, so that you get the answers out of it that you need to drive your business forward.
Great.
And then
Final thought?
what you need is a little different from city to city. And so whatever your particular solution is, there's a customized approach that is required for that still fits into the same model.
Great. Okay, I know we've got a couple of final questions that squeaked into the chat. What I'll do with those is probably just send them around to our speakers, and I'll get you back some individual comments and answers after the session. But again, you know, we really do appreciate everyone who's joined us today for the webinar, looking at data as a service and how that's playing out with different organizations, responding to ways of really helping water utilities embrace some advanced, more complex solutions, and making sure they can optimize how they're approaching their utility functions and operations moving ahead. So thank you again for joining. We will have continued activities thinking ahead to the symposium, so we do want to see everyone back here and hopefully bring some friends too. Thank you for joining.
Thank you.
Thank you.
Thanks very much, Seth. Thank you.
Thanks.